For those who don't know, 3Blue1Brown posted this challenge where we have a clock and a ladybug that starts at the number 12. And every second, it either moves clockwise or counterclockwise to an adjacent number. And the question was, what is the probability that the last number it reaches is the 6? Let's say that the probability that it reaches 6 last is p. And let's also say that the probability that it reaches 1 last is p1. Probability that it reaches 2 last is p2. And p3, so on. And because it's symmetric, we could say the same thing for these other numbers that are on the other side of the clock. So these are all the probabilities that the ladybug reaches these numbers last. So let's consider what happens after one iteration. So after one iteration, the ladybug could either move to the 11 or the 1, right? But in either case, what looked like 5 to 12 now looks like 6 to 1. So given that the ladybug is either at 1 or 11, the probability that it reaches 6 last now becomes equal to the probability that the ladybug reached 5 last when it was at 12. So we could say, because it's certainly either at 1 or 11, that p equals p5. Let's say that the probability that it reaches either 2 or 10 after 2 iterations is lambda 2. And we know that this is the farthest it could go after 2 iterations, because anything else, any other combination, would cause it to go back. So from the perspective of either 2 or 10, what was 6 now looks like 4 from the perspective of 12. So we could say that given that the ladybug is either at 2 or 10, the probability that it reaches 6 is now equal to p4. So we could say lambda 2 times p4 plus the probability that it reaches 6, given that it didn't reach either 2 or 10. And the probability that it didn't reach 2 or 10 after 2 iterations is 1 minus the probability that it does reach 2 or 10 after 2 iterations, which was lambda 2. But because we already found that p equals p5, we know that the probability that it reaches 6 from any other point closer to 12 than 10 or 2 is still p, because p equals p5. So we can just simply solve for p4, and we get lambda 2p equals lambda 2p4, so we get p equals p4. And then we can do something similar for 3 or 9. Let's say that the probability that it reaches either 3 or 9 after 3 iterations is lambda 3. So we have p equals lambda 3 times p3. Given that the ladybug is either at 3 or 9, the probability that it reaches p last is now p3, because it looks the same as the probability that it reaches 3 last from the perspective of 12. So we could say lambda 3 times p3 plus the probability that it reaches the last 6 last, given that it is not at 3 or 9, which is p, because at any other number we already found that p4 and p5 equals p. So we know that at any other number the probability is still p. So by a similar argument, we get that p equals p3. So you could see the pattern. We could do the same thing for p4, or lambda 4. P equals lambda 4 times p2 plus 1 minus lambda 4 times p, which implies that p equals p2. And then for 5, we get p equals p1. Okay, so we know that the ladybug has to reach somewhere last, but we know for sure that it cannot reach 12 last because it started at 12. So we could say that the probabilities that it reaches any number last which is 2 times P1 plus P2 plus P3 plus P4 plus P5, and the 2 is because there's 2 of each number here, plus the probability that it reaches 6 last, which is P, is equal to 1. But we found that all of these were equal to P, so this is just 5P, so 2 times 5P is 10P, plus P equals 1, so 11P equals 1, implying that P equals 1 over 11. So all we did was call what we wanted a variable, and then just call everything else other variables, and then use symmetry to relate the variables to themselves, and use algebra to solve for them. The other thing is this process is generalizable. So for any symmetrical clock, meaning that if it has a line of symmetry here, given n total numbers, we could say that the probability of reaching any point other than the point that it started with is P equals 1 over n minus 1. And of course, the probability that it reaches the point that it started with is 0. A common misconception is that the proximity of 1 and 11 would somehow make it less likely to reach them last than it would 6. But the reason why that's not true, the reason why all of them have the same probability, is because if you think about it, in order to reach 6 last, the Ladybug would have to go all the way to 7 or all the way to 5. And now that it's at 7 or 5, 6 is in the proximity. So it would have to avoid 6 the same way it avoided 11 or 1 in the first place. So it would have to go all the way back and then to the other side, the same way that in order to land on, so let's say 11 last, it would have to move all the way away from 11, right? So it's the same concept, because in order to reach 6 last, it has to avoid the proximity of 6 the same way it avoided the proximity of 1 or 11 to reach them last. So that's my best explanation for why, the intuition for why all of them have the same probability. Yeah, I didn't see anyone else make a solution to this, and I just had a moment of inspiration when I saw the video, so I thought I'd just share my solution because I thought it was pretty cool. But yeah.